Hi everyone, so today we're going to be looking at the first lesson of the cosmology chapter, chapter 20. We will look firstly at astronomical distances and the Doppler effect. So we'll be talking about the astronomical unit, light year per sec, what we mean by stellar parallax and parsec. You will be able to use this equation to calculate the distance in parsecs. We will look at the cosmological principle and what it means. We'll also look at the Doppler effect and the Doppler equation, how to use it to calculate relative speeds and so on. To start with, first, we will have a lot of keywords throughout this lesson, so you need to keep a list of every single definition. So we'll start with the astronomical unit. Now, astronomical unit is simply the average distance from the Earth to the Sun. You need to be able to define what we mean by it. And why do we even use different units for big distances? Is the reason behind it is because the distances are too big and therefore they don't really look good in meters. So we tend to use different units for really long distances that involve space. So one astronomical unit is actually equal to 150 million kilometers. You can convert that to meters and you need to remember this. So why is it the average distance from the Earth, from the center of the Earth to the center of the Sun? It's because we know that the Earth moves in an elliptical orbit with the Sun as one of the foci. So we kind of take the average distance for that. Now, we tend to use astronomical units. So one astronomical unit is 150 million kilometers. So we tend to talk about distances in the solar system in terms of astronomical units. And you can see an image here that shows some of them, some of the astronomical unit distances from the Sun to the different planets in our solar system, which with Mercury being 0.4 astronomical units, Venus 0.7, the Earth obviously 1 astronomical unit because we define it as the average distance from the Earth to the Sun, and then from there it increases. Then we have the light year. Now, this is a distance measurement, not time, because it says light years. Many people confuse it with time, but it's actually got to do with distance. So the definition of a light year is the distance traveled by light in vacuum in a time of 1 year, hence why the name light year. What is the speed of light? We already learned that in chapter 11, I think. Yeah. So that's 3 times 10 to the 8 meters per second, or 300 million meters per second. And we know that 1 year in seconds as well is given to you in the formula booklet. So if you don't remember it, just use it from the formula booklet, or you can quickly calculate it. So you have 365 days times 24 hours each day times 60 minutes times 60 seconds. And if you want to know the distance of 1 light year, well, we know that speed is equal to the displacement divided by time. So displacement is speed times time. So if you multiply these values together, this one is a bit, I think this one is rounded to take into account the leap year as well in terms of the formula booklet, the value that it gives you. And you should get an answer of 1.46 times 10 to the 15 meters. Now, this is given to you as 9.5 times 10 to the 15 meters in the formula booklet. You don't have to memorize it, but you need to know that light year is a measurement of distance and not time. And it's easy to work out and show it because you know that how to calculate, if you know speed and time, you know how to calculate distance. Now, this is used mostly to express distances to stars or other galaxies. And in reality, actually, our Milky Way, so our galaxy, has a diameter of about 100,000 light years. So the diameter of our Milky Way. So yeah, you can see that from there it's very useful to find the distance between stars and different galaxies. Okay, so the parsec is another way of looking at distances. Before I define the parsec though, we will need to introduce something new about degrees. I don't know if you already know them or not, depending on what you're doing in maths. But we know that in a circle we have 360 degrees. Now, each single degree can be split into 60 more divisions, and we call that arc minutes. So there are 60 arc minutes in 1 degree, and then the 1 arc minute we can split into further 60 more fractions, which we call arc seconds. So there are 60 arc seconds in each arc minute. So we come up to the definition that 1 arc second is 1/3600th of a degree. So for the definition of the parsec, I always think it's helpful to always include a diagram to show what we mean by 1 parsec. Now, the parsec is defined as the distance at which the radius of 1 astronomical unit subtends at an angle of 1 arc second. You do need to know the definitions. So the parsec is defined as the distance which the radius of 1 AU subtends at an angle of 1 arc second. So 1 over 3,600 degrees, basically. So the parsec distance is this distance here, the green line that you see. How can we work through it and how can we figure out what 1 parsec is? We'll do that now. Also, like I mentioned before, you can use the diagram to help you with the definition, even if you mess up a bit with your definition. Okay, so now we're going to see how what 1 parsec is equal to by using some trigonometry. And this line is supposed to be a little bit straighter here. So this is a 90-degree angle. So what we have here is 1 arc second of an angle. It's part of the definition. This is the 1 parsec, and this is 1 astronomical unit. So this is all based on the definition. So if I want to know what 1 parsec is equal to, I have opposite over hypotenuse, adjacent. So that will be tan theta is equal to 1 astronomical unit over 1 parsec. So if I want to rearrange for 1 parsec to calculate how much that is in meters, then I need the 1 astronomical unit over the angle theta. And since the angle is 1 arc second, then that's 1 over 3,600. So what we have is 1 astronomical unit, which is we said that that's 1.5 times 10 to the 11 meters. Divide that by ton, 1 over 3,600, and you get 1 parsec as 3.1 times 10 to the 16 meters. Once again, this is given to you in the formula booklet, so you don't have to remember it. Okay, so this is basically the calculation in the way that we're seeing it. And we're going to talk about parallax now. Now, this is a little bit of a fun activity to do. So if you extend your arm out and place your thumb towards the smiley face in the screen, you can view the face with only first your left eye, and then you can view it with your right eye only. Now you're going to notice an apparent shift in the smiley face compared to your thumb by viewing it at different angles. Parallax is actually the apparent shift in position of a relatively close star against the backdrop of much more distant stars. Since there's so what we mean by this is, let's say these were all background stars like that were far away, and we were observing, let's say, one star that's much closer. The stars that are further away will appear to be not moving at all because they appear to be constant in the same spot. However, the closest star will appear to shift in positions depending on where the Earth is and where we're observing it from. So this is what we're going to have a look at now. Also, parallax is something, I don't know if you remember parallax errors, but it's something that we talk about all the time in terms of taking readings. So the same way we said that if you're taking a reading, you need to align your eye with the reading that you're taking. Otherwise, if you take it from a different angle, so if that's your eyeball, by the way, that's your eye looking in different directions. If you take it from different angles, it could give you a different reading because of that parallax, that apparent shift in the position of what you're reading. This is what we mean by parallax error as well. But this is in terms, this will be applying to the calculations in terms of distance. Okay, so let's see how we can use these parsec calculations and how it works through further distances away from us. So, stellar parallax is a technique used to determine the distance to stars that are relatively close to the Earth, so less than 100 parsec. We can use this equation, I'll go through it in a second, but before I go through that, you need to understand how this works. So if we look at the Earth's position, for example, in July, so the diagram, in the diagram here. Now, in that position, the nearby star appears to be in this position here. So you stretch out the line. So this is the nearby star here, but it appears to be, if you compare it to the background stars, it appears to be in that position compared to them. Now, when the Earth moves to this position in January, for example, the nearby star, instead of appearing to be where it is, it appears to be in this position. Now, with the lines crossed, you can see that that's where the actual star is. And with precise measurements, they can really find the parallax angle, this angle here, which is labeled as P. So this is the angle here, the parallax one. This angle is always measured in arc seconds. So when we talk about the angle P, we mean the angle which is measured in arc seconds. So you need to make sure that the angle is in arc seconds when you do the calculations. So the distance to the nearby star, D, is given in parsecs. So when you calculate it, so if you use the value of P in arc seconds, you get the answer in parsecs. This is kind of similar to what we saw briefly in the previous part of this video when we're looking at what parsec is defined. So yeah, like I said, this is limited to stars that are less than 100 parsecs away, and that's due to the fact that obviously we have the further away the star is. So if the star was here, then the angle will get much smaller and smaller, and it's very hard to measure. Even using very, very precise equipment will not get a very precise answer. It won't be measured accurately. So this is how we can calculate. So this equation is quite important. So remember, D is the distance in parsec if the angle is in arc seconds. Okay, so going back to the learning outcomes, we looked at the astronomical unit, the light year, and the parsec. And we also talked about the stellar parallax with distances, the parsec, and the equation where P is the parallax in arc seconds and D is the distance in parsec. We will have a quick look at the cosmological principle and the Doppler effect and equation. Okay, so for the cosmological principle, we need to kind of forget that we are the center of the universe, since we are actually not. It would be nice to think that, but you know, there's nothing special about the Earth. Is just because there's life on Earth doesn't really change the fact that the Earth is just simply a rock, a massive rock. So what we will look at is the cosmological principle. It's basically an assumption that the universe is homogeneous and isotropic and that the laws of physics are basically universal. So it's homogeneous because every part is the same as every other part around you. So matter is distributed uniformly across the universe. So that means the density of the universe is uniform. And we say that it is isotropic because the universe is the same in all directions to every observer. So it will look the same in every direction that you look at it. That means that there is no center or edge to the universe. And this actually means, so the fact that it's homogeneous and isotropic means that the laws of physics are universal. It's a very strong idea to have. It means that we can apply everything that we know of physics on Earth to the solar system and the rest of the universe. So just make sure that you know what we mean by homogeneous, isotropic, and the fact that the laws are physics are universal. It's the only part on cosmological principle that you need to know either way. We're going to start with now move on to the Doppler effect and how we can analyze it. So let's look at what Doppler effect is. Now, Doppler effect is a phenomenon that you observe whenever a source of wave is moving with respect to an observer. So now, if you imagine that you have two people just standing there. Now, obviously, they won't observe any change in sound or anything like including if they were holding flashes of light. They wouldn't observe any change in any type of wave relative to each other because they're both stationary. However, if you have one of the people moving, then that's when you will expect to watch to see a Doppler effect. Okay, it's not picking up anyway. So it applies to all types of waves. So this can happen to sound waves. It can happen with electromagnetic waves, so like radio waves, light, and so on. And it can happen to more than just that. Anyway, so we'll move on with this. Actually, before I move on, so if we consider two people that we see here, so we see the girl and the boy. They're both stationary. However, the police car is moving. Now, if the police car is moving towards the boy, even though the source itself has the same frequency and wavelength that it emits, of wave that it emits, so this is very important to actually get. Even though the source is moving, it's not moving relative to itself, and it can't, right? So the actual frequency sound that the police car emits is constant from the source. It's the way we observe it that causes it to change. So we get the observed sound frequency that we hear because it's moving towards us, but the actual sound's frequency in the source does not change. It's just the way we perceive it. So that's why it's a phenomenon observed by a person if you have a source moving relative to you. So now since it's approaching the boy, you can see that the waves are getting closer together. Remember, these are wavefronts, so the distance between the wavefront is a wavelength. So if they get closer together, that means the wavelength has decreased. So if a source is approaching you, the wavelength decreases. But on the other hand, so basically what you have is like a wave that squashes as the car is approaching you. Now, the speed of the wave remains constant. And so that means that since speed is equal to frequency times wavelength, if this is constant, then that means if the wavelength decreases, then the frequency has to increase to keep the speed constant. So frequency increases. So that's why we hear that high-pitched sound when a police car or an ambulance is actually coming towards us. We hear the really high pitch. Now, if we look at the girl, though, as the car is moving away from her, the wavelength increases. So if a source is moving away from you, a light source, whatever wave source you have, the wavelength appears to increase, therefore the frequency appears to decrease. Remember, the speed of the sound is actually constant in this case. Well, it always was constant. It's just that the frequency and the wavelength appear now differently to us. So remember, the speed is constant. Oops. So this is where you experience the less pitch sound, because the frequency is lower. Remember, frequency is related to pitch. Loudness or brightness is related to amplitude. This is something that you learned quite a while ago as well in earlier years of your science course in year 7. Okay, so this is how it appears when no one is moving. So if the source of the sound, so in this case it was the police car, if it was just parked there between two people, both people will receive the sound the same way, because no one's moving. Now, if the source starts moving, and in this case it's moving to the left, it appears to squash those rings. And remember, those rings are not rings, they're actually wavefronts, so the distance is between them is the wavelength. And you can see that it's the same all around, so there's no apparent change in wavelength or frequencies. Only when the source starts moving that it causes the observers in the direction that it's moving in to appear that there is a shift in sound. Now this can happen with light too, and that's what we tend to use to analyze what happens with the light coming from stars. And that helps us know whether some of the galaxies are moving towards or away from us. So on the other side, you will expect the observer to, if we were talking about light, and I will do actually a pause here to take you back to a quick reminder. Just to remember that the only thing that we can get from stars and galaxies in general is the light that's coming from the stars. Now, electromagnetic waves are transverse waves, okay? Just a quick reminder of that. And light is an electromagnetic wave. So we can only analyze the light, so we are only interested in the light in this case. Just to remind you that electromagnetic waves are like electric and magnetic fields oscillating at right angles to each other. There are different types of EM waves, and we classify them by wavelengths. So something that we've looked at when we looked at electromagnetic waves in chapter 11. Also, the absorption light spectrum that has a series of dark central lines is something that we've seen quite recently. So these are basically the lines of light, visible light, electromagnetic wave that the gas absorbs around a star. So it's the photons pass through the gas, some get absorbed by the gas atoms and they get excited. That's what appears as those missing lines there. So that's a quick reminder, because we will be looking at that in terms of how it shifts to either side based on the Doppler effect. And that's what we use actually to figure out whether Big Bang Theory is a bit, has a relevance. Okay. I will skip the excitation and the excitation because we just done it recently, and I'll just proceed to the next part. So, a very quick reminder that we have the electromagnetic waves, and that as we go from this side to this side, the wavelength increases. Now, visible light can be split into its own colors of the spectrum, the rainbow. So you have red, orange, yellow, green, blue, indigo, and violet. Now, red has the longest wavelength, and violet has the shortest wavelength. That's important because it's something that you will need to be able to realize and connect together when we talk about redshift and blue shift. Now, the Doppler shifts in starlights. When a star is moving away from us, when we receive the light, the wavelength increases. So if it increases, that means that we will get the light coming from it a bit more redder, so shifted to the red. Now this is the unshifted one. This is something that we get from by looking at the absorption line spectra from stars and comparing it to the unshifted one that is from, for example, the emission spectrum in a lab. Okay, so that's where they collect it basically. So the unshifted one is the one that was collected from the emission spectrum in the lab. The other two coming from distant galaxies. So determining the absorption spectrum of a specific element in the lab, that's how they do it. And then the same spectrum is observed in light from a distant galaxy. So these two are coming from distant galaxies. Now, which one shows redshift and which one is moving away or towards us? Well, if we look at it, this line here actually shifted towards the red end of the spectrum, and you can see that every single line shifted by the same exact amount. So that means that this is a red shift. Since red has a longer wavelength, that means if it moved towards the red, then it's red shifted. So the wavelength increased. If we look at the other diagram though, the bottom, we can notice that the line actually moved away from the red towards the blue. So did this by exactly the same amount once again. You can see that well, if I done it with a ruler, it will show better. So you can see the shift is towards the blue side, so we call this the blue shift. And once again, remember that blue has a lower wavelength, smaller wavelength, so the wavelength has decreased in that case. So where is it moving towards? We'll talk about that in a second as well. So I usually always remember the initials. I call it RMIVOXG. I just remember it that way easier. You can have your own techniques to remember this. But the thing that really helps me is that these are, and I always remember obviously that the radio waves have the longest wavelength, so that means everything else decreases from there. So the easiest way I remembered, it helped me remember how to, which one has the longest and shortest wavelength, is the fact that this starts with R, and so should the colors of the rainbow start with R, which is the red. So I thought that I'll mention that before I continue. So we said that since the wavelength increases, that means the object is moving away. So the galaxy, in this case, is moving away. In the blue shift, since the wavelength is decreasing, then we have a blue shift. Sorry, already said that. We actually have the galaxy moving towards us. So since it's moving towards us now, the waves are squashing between us instead of stretching out. You can think about it as two balls and a spring in the middle. So if you were holding one fixed, so let's say this is the Earth, and you're holding this fixed, if you start pulling the planet away or whatever it is, then it will stretch this slinky, so that means the wavelength increases. So between each coil of the slinky you have more distance. So it means it's moving away. Automatically, if the wavelength increased, then you stretched it, you moved it away. Now, on the other hand, if you pull the ball this side, it will squash the Earth with the ball together, and basically you have more slinkies squashed together, which means that you have a smaller wavelength between them. To apologize for my drawings, I'm not very artistic today. So then you know that you move the ball closer together. That means that the wavelength decreased. I hope this helps a little bit with remembering things and trying to figure them out or work around them. Okay, so then how do they move on from here? What do they do with this? Okay, we know that some galaxies are coming towards us, but most of them are moving away from us. This is something we'll talk about in the next lesson, though. Now, what can I do in terms of calculations? How can I figure how fast they're going, or why how the change in the wavelength shift is basically taking can be used to calculate that. So the change in the observed wavelength, what we call the Doppler shift, so that's quite an important part there, depends on the speed of the waves in the medium as well as the relative speed of the observer and source in the medium. So what you have it here is the equation that you could use. Basically what it means that you could use the change in the observed wavelength divided by the wavelength measured in the lab. So the actual, the source's wavelength that you're meant to receive, which we know because we already measured that in the lab, is equal to the speed, the relative speed to the between the observer and the source, and the speed of light in vacuum. Or you can use the frequencies instead, the change in the observed and measured frequency divided by the frequency of the source, which is the one that we already know from the lab. Remember that you can always calculate the frequency of wavelength since you already know the speed, which is 3 times 10 to the 8 in this case. It could be used for some other things too, but we'll talk about that if we have enough time at the end of the course. Frequency times wavelength is equal to the speed of light if we're talking about EM waves. So if I know the frequency, I can calculate the wavelength, or the other way around, it doesn't really matter. And again, it's equal to VC, which is the same thing. So, like I said, delta lambda is the change in wavelength that the observer sees. So basically the change in the, so if you receive, let's say, a frequency of 700 hertz, by the way, this is extremely tiny, I'm just giving an example. And in the lab, you know that frequency is supposed to be 50 hertz, then you know the change between them basically is the delta lambda. Divided by the source wavelength, the one that we already know because of the lab measurements, so in the laboratory. And V is the speed, is the magnitude of the relative velocity between the source and the observer. That's quite important. And C is the speed of light through vacuum. So if we look at the equation, the faster a source moves, the observed change in wavelength. So delta lambda is really directly proportional to V. So the faster a source is moving away, the bigger the observed change in wavelength. So if you have the light, I'll actually go to it. So the faster, the bigger. Okay, so if we go to this one quickly. So you have you can see the spectral lines observed from a distant galaxy. So these are the spectral lines. The black lines in the emission, it's absorption spectra, correspond to specific elements. And since we have those elements on Earth, we can compare the transition spectra when not moving with the ones that we receive from the actual distant galaxy. So here you can see how the line shifts from there to there. However, what we if that galaxy was moving away from us faster, we will notice the shift even greater. So it would be, instead of being there, that point would have been there, and every other line would have shifted by the same exact amount. So that's an important distinction here to include in terms of noticing whether something of what you can actually gather from the absorption spectra. So you can gather two things: whether a galaxy is moving towards or away. It's actually three things. So you can figure out whether something's moving towards or away from you. You can also figure out if it's moving away from you faster than another one. So the speed at which it's moving at. You can do calculations obviously too. And the third point that you can notice from it is the actual elements that you are investigating. in a specific star, in a specific galaxy, or in the general in the galaxy there. Okay, so that's it. That's just about it. So if you get the change, then you can figure out basically the value. Also, to remind you that when we are using this equation, so this is lambda, the wavelength that we use here is the wavelength that we measure in the lab on Earth. So it will be wise to get this value, which is, I think, 420 says there. So that would be your 420, sorry, the change between this value and this value, whatever this one is. No, that's 390, sorry, 395. I couldn't see that clearly. So this one is 440, sorry. So yeah, you'll take the value in the lab one, so 395, and you will divide it by the change between this value, basically 390 and 440. So that would be 35 divided by, and remember, you don't have to convert the units here because they actually cancel out. And then, yeah, you multiply it by the speed of light to find the speed of the actual distant galaxy, if it's moving towards or away. Here we notice that it's redshifted, so it's definitely moving away, hence why the wavelength increased. Okay, so coming back to the learning outcomes, we talked about the cosmological principle, how the universe is homogeneous, isotropic, and the laws of physics are universal. You need to be able to explain these terms as well. They do get asked a lot in exam questions. Doppler effect, what it is, Doppler shift of electromagnetic radiation, so that's why we just focus on the EM radiation here. And the Doppler equation for a source of EM radiation moving relative to an observer. So you should be able to apply all of those after this lesson.